Okay, hello everyone in a new video. So we have reached part 5 of chapter 11, which is the chapter of pressure in liquids in the third unit of mechanics. So in this part we are going to solve some exercises on what we have explained previously. So exercise number 7. To determine the pressure of a confined gas, a group of students made the two following experiments, given that G is equal to 10 newtons per kilogram, which means that these experiments are being performed on the surface of Earth. Number 1, first experiment, determination of the atmospheric pressure. The group filled the tube T completely with mercury of density ρ is equal to 13,600 kg per meter cube. So this is the density of mercury. Then turned it upside down and immerse it in a container containing mercury. The level of the mercury dropped down and settled at 75 centimeters above the free surface of the mercury that's found in the container document 1. So they mentioned document 1, now we can use it. Notice that till this moment they didn't mention anything about document 2, we are not allowed to use it. So this is the tube T, and this is the container containing mercury. This is mercury. So after performing this experiment, the students obtained the following. So this is the tube T immersed in mercury. After turning it upside down, the level of mercury dropped down to 75 centimeters. Let's denote this height to be h is equal to 75 centimeters. Knowing that centimeters is not a unit of height or length, in order to convert from centimeters to meters, we simply divide by 100. Then 75 divided by 100. So the height is given by 0.75 meters. And here notice that above the point C, as indicated, we have vacuum. This is important. Now 1.1, so we are in 1.1. What is the value of the pressure C at C? Why? So since we are interested in determining the pressure, we consider the point C and we look upward. Notice that C is being submitted to the pressure of vacuum. So let's say that C is submitted to the pressure of vacuum. And we know that vacuum is a part of space that is free from everything, including air and the three states of matter. So in this case, the pressure is given by 0. So the pressure of vacuum, which is 0. Then the pressure at the point C is equal to 0. Now 1.2, determine in Pascal the value of the pressure B at B. And because we are interested in determining the pressure, we consider this point, which is the point B, and we look upward. So notice that the point B is submitted to two pressures: the pressure due to the layer of this liquid, which is mercury, and to the pressure exerted by the point C, which is 0. Now here they are telling me the value of the pressure at B. So it's not the pressure due to mercury, nor the pressure due to vacuum, but the total pressure at the point B, which is mercury plus vacuum. In this case, the vacuum is 0. So first, let's say that B is submitted to the pressure of mercury, and to the pressure of vacuum. So they usually give half a mark for this statement. This statement in this case is important. So the total pressure at the point B is the pressure due to mercury. Since the symbol of mercury is usually denoted by Hg, so let's denote this pressure by PHg plus the pressure due to vacuum, which is Pc. Now because Hg is mercury, so this is the pressure due to a liquid, which is given by the density of the liquid times G times H. So the density of this liquid, which is mercury, is denoted by ρ, multiplied by G multiplied by the depth at which we are calculating this pressure, which is 75 centimeters, and we have denoted this pressure by H, plus the pressure at the point C, which is the vacuum, which is 0. Now the density of mercury in the SI is given by 13,600, the value of G is given by 10, and the value of H is given by 0.75. Plugging this on the calculator, then the total pressure at the point B is given by 102,000. Since all of these are expressed in the SI, so the value of PB will be in the SI, which is a Newton per meter square, and usually this unit is denoted by Pascal. Then the total pressure at the point B is given by 102,000 Pascal. So let me write here, corresponding for the first experiment, the total pressure at the point B is given by 102,000 Pascal. Now in 1.3, the pressure at A and the pressure at B have the same value Y. So always such type of questions are answered using or justified using the rule of 3, which is given by same liquid at equilibrium, and either we say same pressure or same horizontal level. Since we are interested in justifying why the points A and B have the same pressure, we will eliminate this, and our answer would be same liquid at equilibrium and same horizontal level. So indeed that this experiment is being performed at equilibrium, and they are in the same liquid, so which is mercury, and they are in the same horizontal level as indicated here in this document. So let's say that since A and B are in the same liquid, at equilibrium, and in the same horizontal level, then A and B are submitted to the same pressure, then in this case we have that the pressure at the point A is equal to the pressure at the point B. Now 1.4, deduce the value of the atmospheric pressure, P atmosphere. Here let me write that pressure at the point A is equal to the pressure at the point B. So we need to deduce the value of the atmospheric pressure, and by deduce it means that we need to use the previous part. In the previous part we have determined an equality between the pressures at the point A and B. Knowing that we have the value of the pressure at the point B, so we already know the pressure at the point A, but what's the link between the pressure at the point A and the atmospheric pressure? Since we are interested in determining the pressure, we consider the point A and we look upward. Notice that A in this case is open to the atmosphere, so A is being submitted to the atmospheric pressure. So indeed the relation between the atmospheric pressure and the pressure at the point A is that they are equal. But first, let's justify this and say we are in part 1.4. A is submitted to the atmospheric pressure, so this statement in this case is important because it's the link between the pressures at the point A and the atmospheric pressure, so they usually give it half a mark. So the pressure at the point A is equal to the atmospheric pressure, but we know that PA is equal to PB, but the value of PB is given by 102,000 Pascal. Then in this case the pressure at the point A is given by 102,000 Pascal, and finally the atmospheric pressure is given by 102,000 Pascal. So this result is important. The atmospheric pressure is equal to 102,000 Pascal. Now number 2, second experiment, determination of a pressure of a confined gas in the tube. After the determination of the atmospheric pressure, which is corresponding to the first experiment, the students inject in the tube a certain quantity of gas. The level of the mercury in the tube drops down again to become 70 centimeters above the free surface of the mercury that's found in the container, document 2. So they mentioned document 2, now we can use it. So here also we have mercury. Now in the second experiment, the students have injected here in the tested tube T from, let's say from this point, they have injected a gas. Now this gas is said to be a confined gas because it's found here. Now this gas will exert a pressure at the point C. For this reason, the level of mercury will drop down from 75 centimeters to 70 centimeters due to the pressure exerted by the confined gas to the surface of this liquid here, which is mercury. Now in 2.1, determine in Pascal the new value of the difference in pressure PB minus PC. So here the difference means the variation, and the variation is usually denoted by delta P. We know that delta P across any 2 points is given by the density of the liquid times G times H. So this delta P is the difference between the pressure of 2 points. So we always start by the point which is located at a horizontal level lower than that of the other point, which is the point B, and the other point is the point C. So for sure that PB minus PC represents delta P. Now it is equal to rho L multiplied by G multiplied by H. But what does H represent? It's the difference between, the difference between the 2 points, which is given by 70 centimeters. So let's denote this difference to be H prime, since we have used H for the first experiment. Then 76 centimeters, knowing that centimeters is not the SI unit of height. In order to convert from centimeters to meters, we divide by 100. So it's given by 0.76 meters. Now we need to determine this difference, which is given by PB minus PC, which is in this case given by delta P, which is equal to the density of the liquid times G times H. The liquid is given by mercury, and the density of this liquid is denoted by rho multiplied by G. H, which is the difference between the points B and C, is given by 70 centimeters, and it's denoted by H prime. Now the value of rho is given by 13,600. The value of G is given by 10, and the value of H prime is given by, sorry, this is not 76 centimeters, this is 70 centimeters. Sorry, I have made a mistake here. Now plugging this on the calculator, then the value of the difference PB minus PC is given by 95,200. Since all of these are expressed in the SI, so this difference will be in the SI. So notice that this difference is due to the difference of pressures. So in order for this quantity to be in the SI, separately PB must be in the SI, which is given by Newton per meter square, and this Newton per meter square. So this value is given by Newton per meter square, and usually this unit is denoted by Pascal. For this reason they are telling me determine in Pascal. 95,200 Pascal. Then PB minus PC is equal to 95,200 Pascal. Now in 2.2, so here let me write that PB minus PC is equal to 95,000 200 Pascal. 2.2 deduce the value of the pressure P of the confined gas in the tube. So here we need to determine the pressure of the confined gas. So the confined gas being found here, and notice that the point C is being submitted to the pressure of the confined gas. So let's write, we are in part 2.2. C is submitted to the pressure of the confined gas. So what does this mean? If we are able to determine the pressure at the point C, we are done. And notice that here in part 2.2 they are telling me deduce, which means that we need to use the previous part. So in the previous part we have determined PB minus PC, the difference, which is equal to 95,200 Pascal. So what's the relation between this and PB minus PC? Notice that since C is being submitted to the pressure of the confined gas, then if we are able to find the pressure at the point C, we are done because we have determined the pressure of the confined gas. So we are interested in determining the pressure at the point C. So what's the type of this equation? If PB is known, then the type of this equation is linear equation. So it's left to know the value of PB and one unknown, and the unknown is given by PC. What about the pressure at the point B? So notice that because in the second experiment, B and A are still in the same horizontal level, for this reason PB will be equal to the pressure at the point A, and we have determined in the second experiment that we have determined the first experiment that the pressure at the point A is equal to the atmospheric pressure. So let's say the pressure at the point B is equal to the pressure at the point A, which is equal to the atmospheric pressure, and it's given by 102,000 Pascal. So now replacing the value of PB in this linear equation, we have that 102,000 minus PC is equal to 95,200, knowing that we are interested in determining the value of PC. So now I repeat that the type of this equation is a linear equation and one unknown. The unknown is PC. How do you solve this equation? We put PC on one side and all the numbers on the other side. So this is the equal. Now keeping minus PC in its place, and here we have 95,200. However, dragging this number to the right hand side, it will gain a minus sign, so it will be given by minus 102,000. So minus PC is equal to, plugging this on the calculator, then it's given by 6,800. Sorry, minus 6,800. But notice that we are interested in determining PC and not minus PC. In order to get rid of the minus sign, we multiply both sides by a minus sign, then it will be given by PC is equal to 6,800. Since everything previously is expressed in the SI, which is expressed in the SI, so the unit of PC will be given in the SI, which is given by Pascal. Then the pressure of the confined gas is given by 6,800 Pascal. Then exercise number 8. We would like to determine graphically the depth h in meters of a water in a well. For this purpose, we place at the bottom of the well a manometric gauge that gives the total pressure at the point B of the bottom. So given the density of water is equal to 1000 kg per meter cube, let's denote this density by raw water. Then the density is already given in the SI. And the atmospheric pressure is given by 103,360 Pascal. So the atmospheric pressure is given by 103,360 Pascal. and the G is equal to 10 newtons per kilogram, which means that we are performing this experiment on the surface of Earth. Okay, they didn't mention this figure, but for sure we can use it. So number 1, give the value of the pressure P0 at A. So whenever we are interested in the pressure, we always look upward, considering the point A and looking upward. So notice that the point A is open to the atmosphere, then A will be submitted to the atmospheric pressure. Here also let me explain the figure. So this is the well, and this is the manometric gauge here at the point B. So this is the manometric gauge, let me say M gauge. So the aim of this exercise is to determine the total pressure at the point B. This liquid is given by water, and here as you can see that A is being opened to the atmosphere, so it will be submitted to the atmospheric pressure. So they are telling me to give the value of P0 at A. First, let's explain that A is being submitted to the atmospheric pressure. So let's say that A is submitted to the atmospheric pressure. In this case, this statement is important, and they usually give it half a mark. So the pressure P0 at the point A is equal to the atmospheric pressure, is equal to 103,360 Pascal. So for this reason, P0 is equal to 103,360 Pascal. So here let me write the value of P0. The pressure at the point A is given by 103,360 Pascal. Now, number 2, give as a function of H the pressure P1 exerted by water on the point B. So considering the point B and looking upward, here don't get confused. Above the point B there is a capsule which is the manometric gauge, but this doesn't exert any pressure at the point B. So considering the point B and looking upward, we notice that B is submitted to the layer to the pressure due to the layer of water and to the atmospheric pressure that is being exerted at the point A and transmitted to the point B according to Pascal's theorem. However, we are only interested in determining the pressure P1 exerted by water. So the pressure P1 exerted by water, since it's the pressure due to a liquid, so it's given by the density of the liquid times the G times the depth. Now the density of this liquid, which is water, is denoted by rho W, multiplied by G, multiplied by the depth at which we are calculating this pressure, which is given by H. Now here notice that they are telling me express as function of H. The value of P1 must include H as a variable, so let's keep H as a variable. Now the value of rho W is given by 1000 and the value of G is given by 10, so we keep H as a variable. Now 1000 multiplied by 10 is given by 10,000 H. So the value of P1, which represents the pressure exerted by water at the point B, is given by 10,000 H. And notice that here I didn't include any unit for P1 since P1 is expressed as a function of another variable, which is H. And now in number 3, show that the total pressure at B is expressed in Pascal, so in the SI, is written in the form of P is equal to 10,000 H plus P0. So we are interested in the total pressure at the point B. So notice that, since we are interested in the pressure, we consider this point and we look upward. So the point B is submitted to two pressures, the pressure due to this liquid which is water, and to the atmospheric pressure. Now let's write that B is submitted to the pressure of water and to the atmospheric pressure. So in this case, this statement is important and they usually give it half a mark. So the total pressure at the point B, which is denoted by simply P, is equal to the pressure exerted by water, which is given by PW. Sorry, it's given by P1 plus the atmospheric pressure. Now, the value of P1 is given by 10,000 H, whereas we have proven in part 1 that the value of the atmospheric pressure is equal to P0. So now replacing the atmospheric pressure by P0, we got. So this is the required relation, that the total pressure at the point B, which is denoted by P, is equal to 10,000 H plus P0. So we have that P is equal to 10,000 H plus P0. And let me make some space here. Now in number 4, trace on the graph paper the graph of the variation of delta P is equal to P minus P0 as a function of H. So first, let's construct the axis that allows us to trace this graph, which shows the variation of delta P as function of H. So this is the y-axis, this is the x-axis. Now always in physics, the x-axis and the y-axis must be labeled by physical quantities. So notice that here they are telling me the graph of the variation of delta P as function of H. So the first quantity that comes after the variation is delta P, and then it is followed by H. So because delta P is the first to come after the variation, then this quantity represents the y-axis. So this is delta P, and this is H. Moreover, this can be verified using the scale. So let me write the scale here. Now, so on the abscissa represents the x-axis. Each 1 centimeter corresponds to 0.1 meters, and for the y-axis, now the y-axis is said to be the ordinate. Each 1 centimeter corresponds to 1000 Pascal. So notice that here, if we compare this x-axis with this x-axis, which is labeled by the physical quantity H, we notice that meters is in agreement with this physical quantity, which is H, so H must be expressed in meters. And as for the y-axis, each 1 centimeter corresponds to 1000 Pascal, and we know that Pascal is the unit of pressure. And we always start by the origin. Now the next step is to divide these axes. So notice that here in the x-axis they are telling me 1 centimeter, so we are considering this division on my graph paper to be 1 centimeter. So each 1 centimeter corresponds to 0.1 meters. So this is 0.1, 0.2, 0.3, and now as for the y-axis, each 1 centimeter corresponds to 1000 Pascal. So this is 1000, this is 2000, this is 3000, and this is 4000. So notice that these axes, these values doesn't carry any unit because already the unit is included on the axis itself. So, and let me make it this clear that this is H in meters, the height. Now yet we didn't trace the curve that shows the variation of delta P as function of H. Usually in order to draw this curve, a table must be given that relates the values of delta P and H. In this case we don't have a table. However, we can determine the value of delta P. So we know that delta P is equal to P minus P0, but the value of P is given by 10,000 H plus P0. So replacing the value of P in delta P here, so we get that 10,000 H plus P0, and we don't forget the minus P0 here. Now P0 goes out with minus P0, then the value of delta P as function of H is given by 10,000 H. So delta P is equal to 10,000 H. So what does this equation tells us? Whenever we know the value of H, we know the value of delta P. So this allows us to plot the curve that shows the variation of delta P as function of H. So notice that this equation is in the form of y is equal to ax plus b. By referring to this axis, we know that x in this case is labeled by H and y is labeled by delta P. So in math, how do we plot such type of equations? This equation corresponds to a straight line. So in math, in order to plot an equation of the form y is equal to ax plus b, we construct the following table given by x versus y, in which the values of x, for example, they are given by 0, 1. Now referring to this equation, we determine the values of y. So replacing x by 0, 1 can determine the value of y. Replacing x by 1 can determine the value of y as well. So we need to construct a similar table, but for this equation, that allows us to plot the following curve. So here, because x represents H and y represents delta P, then the table that we are interested in constructing is given by H versus delta P. So let's say that H versus delta P. So here in math, if this is x and this is y, the values of x usually are given by 0, 1. So how do you know it's 0, 1? Because we take the first 2 points. Here, if we need to consider the first 2 points of the values of H, they are given by 0 and 0.1 and not 1. So let's consider that the values of H is 0 and 0.1. One could, for example, choose another 2 values, let's say 0.1 and 0.3. So H is up to us. Okay, we can choose any 2 points from these axes. Now as for delta P, now we need to determine the value of this point and this corresponding to this point. So let's say for H is equal to 0, now delta P is equal to 10,000 H. Now replacing H by 0, so the value of delta P in this case is given by 0. So here let me write that delta P is given by 0. Now when H is equal to 0.1, so delta P is equal to 10,000 H. So it's equal to 10,000 multiplied by 0.1, which is equal to 1000 Pascal. So in this case, the value of delta P is given by 1000. And we know that it's sufficient in order to draw a straight line. It's sufficient only to consider 2 points. Now when the value of H is given by 0, the value of delta P is given by 0. So the origin is the first point of the curve. Now another point corresponding to the curve, when H is given by 0.1, the value of delta P is given by 1000. So this is another point corresponding for the curve. Now these 2 points allows us to plot the variation of delta P as function of H. So in this case, we can notice that the shape of the curve is a straight line passing through the origin. And here we don't forget finally that there is a title. And the title is given by the variation of delta P as function of H. Now number 5, on a certain summer day, the pressure given by the gauge has the value P total, or P is equal to 105,360. Let me make some space here, Pascal. Now 5.1, we are in part 5. Calculate then the value of delta P. So knowing that delta P is given by the expression P minus P0. Now we are calculating delta P for this summer day. Now the value of the total pressure P is given by 105,360 Pascal, whereas the value of P0 is constant and doesn't change, which represents the atmospheric pressure and given by 103,360. Now replacing P by this value, so here this is given by delta P. Now plugging this on the calculator, then the value of delta P is given by 2000. Since both this and this are expressed in Pascal, so the value of delta P will be also expressed in Pascals. So delta P is equal to 2000 Pascal. So the variation of pressure on this summer day is given by 2000 Pascal. Now 5.2, deduce graphically the depth h of water in the well on that day, and by deduce it means that we need to use the previous part, and they are telling me graphically, which means that we need to use this curve. So let's write as a title graphically. So we need to use this curve in order to determine the value of h. So what's the advantage of this curve? Whenever we know the value of one quantity, we can determine the value of the other. Knowing the value of h, we can determine delta P. Knowing delta P, we can determine h. Since we are interested in determining h, we need to know the value of delta P. Notice that here they are telling us deduce, and the previous part we have determined the value of delta P. So let's say for delta P is given by 2000 Pascal. So 2000 Pascal correspond to this point on the curve, which has a value of h is equal to 0.2 meters. We have h is equal to 0.2 meters. Then the depth of this well is given by 0.2 meters. So exercise number 9. A vessel contains a quantity of water to a height h is equal to 30 centimeters. Then we have that h is equal to 30 centimeters. Knowing that centimeters is not a unit of length, in order to convert from centimeters to meters, we simply divide by 100. Then 30 divided by 100, then this height is given by 0.3 meters. Okay. So at the bottom of the vessel, we place a sheet of metal of negligible thickness and of surface area as is equal to 10 centimeters square. So the surface area denoted by S is equal to 10 centimeters squares. So knowing that centimeter square is not the SI unit of area, so in order to convert from centimeter squares to meter square, we simply multiply by 10 to the power minus 4. Then 10 multiplied by 10 to the power minus 4, then this surface area is given by 1 times 10 to the power minus 3 meter square. The vessel is placed on a horizontal table as shown in the adjacent document. So they mentioned this document, now we can use it. The water in the vessel is at rest, for sure it is at equilibrium. So this is h, which is equal to 0.3 meters. So, and this is the vessel that contains water. So this shaded part is the water. And here at the bottom of the vessel, we have this sheet of metal. So this is metal at the point B. So we have a piece of metal of negligible thickness. So the thickness of this metal is negligible. Now, given that the atmospheric pressure is equal to 75 centimeters of mercury, so here notice that the quantity which represents the pressure is not in agreement with the unit, which is centimeters, because we know that the unit of pressure is given by in the SI Pascal or in Newton per meter square. whereas centimeter represents the unit of height or depth. So from the early beginning we need to rewrite this properly. Since this value carry the unit centimeter, so it represents the length or the height. But which height? Since it's related to the atmospheric pressure, then it represents the atmospheric height. Then the atmospheric height in this case is given by 75 centimeters. Knowing that centimeters is not the SI unit of height, in order to convert from centimeters to meters, we divide by 100. Then the atmospheric height that allows us to calculate the atmospheric pressure is given by 0.75 meters. And the density of mercury is given by 13,600 kilogram per meter cube in the SI. And the density of water is given by 1000 kilogram per meter cube. Now, given that G is equal to 10 newtons per kilogram, which means that we are performing this experiment at equilibrium on the surface of Earth. Now, number 1, pressure at the surface of water. 1.1, the free surface of water in the vessel is plane and horizontal. Why? So, always such type of questions are answered using the rule of 3, and the rule of 3 is given by, we say same liquid at equilibrium, and either we say same pressure or same horizontal level. Since we are interested in justifying why the free surface of water in the vessel is plane and horizontal, then we will eliminate this, and our answer would be because it is in the same liquid at equilibrium and the same pressure. So here we are talking about all the points on the free surface of this liquid and not only the point A. So all of these points are in the same liquid, which is water, and it is at equilibrium and under the same pressure. Why? Because notice that all of these points are on the free surface of water, so they are open to the atmosphere, and all of them are equally subjected to the atmospheric pressure. So let's say since all points of the free surface are in the same liquid, at equilibrium, and submitted to the same pressure, and submitted, let's say, to the atmospheric pressure, then the free surface of water in the vessel plane, and the vessel is plane and horizontal. And now in number 2, so this is 1.1 and this is 1.2. Calculate in Pascal the value of the pressure at the point A of the surface. So whenever we are interested in determining the pressure, we consider the point and we look upward. Considering the point A and looking upward, we notice that the point A is submitted to the atmospheric pressure. Then let's say A is submitted to the atmospheric pressure because they didn't mention so in 1.2, so this statement is important. Then in this case they give it half a mark. And now we wish to calculate this pressure. So the atmospheric pressure here in the given, they are telling us that the atmospheric pressure is equal to 75 centimeters of mercury. So it's the pressure due to a liquid which is given by mercury, so it's the density of the liquid times G times H. The density of this liquid is given by mercury, which is denoted by rho Hg, and Hg stands for the symbol of mercury, times G times the height. But which height? Since we are calculating the atmospheric pressure, then this height must be the atmospheric height, and in this case is given by 0.75 meters. Usually it's given by 0.76 meters, but it's okay. So the atmospheric height, so we use this value and not 0.76. Now rho Hg, the value of rho Hg is given by 13,600, and the value of G is given by 10, and the atmospheric height is given by 0.75. Moreover, plugging this on the calculator, then the atmospheric pressure is given by 102,000. Since all of these are expressed in the SI, so the value of the atmospheric pressure will be in the SI, which is in Newton per meter square, and this unit is usually denoted by Pascal. Then the atmospheric pressure, which represents the pressure exerted at the point A, is given by 100. So let's say that this is okay, so which is equal to the pressure at the point A. So here let's write that PA is given by 102,000 Pascal. And now number 2, pressure at the bottom of the vessel, 2.1. Calculate the pressure exerted by water at a point B of the sheet of metal. So this is the sheet of metal, and we have considered a point B at the sheet of the metal. So we are interested in determining the pressure exerted by water. So notice that since we are interested in determining the pressure, then we consider this point and we look upwards. So notice that B is submitted to the pressure due to the layer of this liquid, to the layer of water, and to the atmospheric pressure that is being applied at the point A and transmitted to the point B according to Pascal's theorem. But notice that here they are telling us to only calculate the pressure exerted by water. So let's denote this pressure by PW. So it's the pressure due to a liquid, which is given by rho L times G times H. Okay, this liquid is given by water, so it's the density of water times G times the depth at which we are calculating this pressure, which is 8H, and the value of H is given by 0.3. So the density of water is given by 1000 multiplied by 10 multiplied by 0.3. Plugging this on the calculator, then the pressure exerted by water on the point B is given by 3000. Since everything is expressed in the SI, so the value of the pressure will be in the SI, which is Newton per meter square, and usually this unit is denoted by Pascal. So the pressure exerted by water on the point B is given by 3000 Pascal. Now in 2.2, deduce the value of the total pressure at the point B, and by deduce it means that we need to use the previous part. In the previous part, we have determined the pressure exerted by water at the point B, and knowing that B is submitted to two pressures, the pressure due to the layer of this water, to the layer of water, and to the atmospheric pressure, then let's say that B is submitted to the pressure of water and to the atmospheric pressure. So in this case, also this statement is important, and they give it half a mark. Let me make some space here. Now we are ready to calculate the total pressure at the point B, which is the pressure of water, so PW, plus the atmospheric pressure, which is actually the pressure at the point A. So we can say that PA. Now the value of PW is given by 3000, and the value of the pressure at the point A is given by 1200. 102,000, sorry. Now plugging this on the calculator, then the total pressure at the point B is given by 105,000. Since both PW and PA are expressed in Pascal, so the value of PB will be expressed in Pascal, which is the SI unit of pressure. So the total pressure at the point B is given by 105,000 Pascal. Now number 3, representation of the pressing force. So here they are mentioning the pressing force, which is the force exerted by the liquid on the sheet of metal at the point B, and this pressing force is due to the pressure exerted. This is due to the total pressure exerted at the point B. Now 3.1, calculate the value of F of the force F vector exerted on the sheet of metal. So knowing that the title of this part is the pressing force, so it's the force due to pressure. And we know that force and pressure are related via the following formula, that P is equal to F divided by S. Knowing that we are interested in determining the value of F, so constructing the triangle of this formula, here because we have divide, then P will be at the bottom, F at the top, as here. Knowing that we are interested in determining F, so putting our hand over F, then F is given by P multiplied by S. Now here we have two pressures. We have the pressure at the point A and the pressure at the point B, but notice that we are determining the magnitude of the force exerted on the sheet of metal, and on the sheet of metal we have the point B and not the point A, so it's the pressure at the point B. Now the value of the pressure at the point B is given by 105,000, and the value of S in the SI is given by 1 times 10 to the power minus 3. So plugging this on the calculator, then the value of F is given by 105. So what does F represent? Here F represents the value of F, which means the magnitude, because we know that the force vector F has 4 properties: the point of application, line of action, direction, and the magnitude. But whenever we drop down the vector, so we are talking about the magnitude. Now since both P and S are expressed in the SI, so the value of F will be in the SI, which is in newtons. Moreover, by referring to the triangle here, so we know that P is expressed in newtons per meter square, and the SI unit of the surface area is given by meter square. So Newton per, if we are interested in determining the unit of F and the SI, okay, we already know that the unit of F is in newtons, but this is a verification. Now putting our hand over F, so the unit of F is given by Newton per meter square multiplied by meter square. Meter square cancel with meter square, so the unit of F is indeed given by newtons. So the magnitude of the pressing force exerted at the point B due to water is given by 105 newtons. Now, just a side remark, if we need to classify this force, whether it's a contact force or force acting at a distance, so we know that the only forces act at a distance are the weight, the electric, the magnetic. Therefore, this force is classified as a contact force. Now 3.2, give the line of action and the direction of the force F. So let's write line of action in this order corresponding for the Pilgrim. So we start by the line of action, then the direction. So we know that this liquid, which is water, exerts pressure at the point B downward, so which causes a force on the point B. So what's the direction and the line of action of this force, of the pressing force? So it's act on the point B vertically downward. So the line of action is vertical and the direction is downward. Now 3.3. Represent f at the point B using the scale 35 newtons 1 centimeter, and hereby represent we need to draw, and they gave me the scale. Knowing that, so the scale is given by 35 newtons corresponding for 1 centimeter. So knowing that our rulers are graduated by centimeters and not newtons, in order to draw a force, we need to determine the length of this force, knowing that we have a magnitude, and this is done by referring to the scale, which is a connection between the magnitude and the length. So because 105 newtons, this is the magnitude, so we will put it under 35 newtons. And now we wish to determine the length. So if we cross multiply 105 multiplied by 1 divided by 35, plugging this fraction on the calculator, then the length of the vector f is given by 3 centimeters. So let's consider a point B. So here they are telling me represent f at the point B. So the force F has a point of application, which is B, acting vertically downward. Okay, sorry. So the length of this vector is given by 3 centimeters. According to this scale, it's worth 105 newtons, and the name of this vector is F vector. So that's it for me in this video, guys. In the next part, we'll complete solving exercises on this